Very nice. Thank you very much for this beautiful countdown. Hello and welcome, everybody. Hello and welcome to Mainz, everybody who is sitting at the BASTA conference in person. Hello to all remote listeners to 1 hour of Rust. This is exactly what we are going to do. This is an evening session. This is a BASTA evening session, and as announced, this session will be in English. And evening sessions at the BASTA are a little bit fun, and they should be a lot of code, and we should have something to discuss, and it isn't as much learning and seriousness as we have during the day. We have fun during the day too, but the evening should be a little bit relaxed. And this session, you should be relaxed. I should write a lot of code, and I'm pretty sure we are going to have a lot of fun. The session was announced, or is announced, to be things that C# could learn from Rust. You all know me at the BASTA as a passionate C# developer. And I am a passionate C# developer. I did a full day workshop here at the BASTA. I did a talk today about C#, but I also have a big heart for Rust. Rust is a super cool language, and therefore I thought we should spend an hour discovering amazing features that Rust have and C# simply doesn't. And that is kind of interesting. I have a second agenda here in my talk. I would like to raise your interest in Rust. So this is not a Rust training, to be very, very specific. I don't want to make Rust developers out of you. That is not possible in an hour. Rust is such a huge and powerful ecosystem and language. It takes more than an hour to learn Rust. But still, I would like to spark a little bit of interest, curiosity in you as C# developers to take a closer look at Rust. So please don't judge this session as to be a complete introduction in Rust. It will not be a complete introduction in Rust. I just picked out some random stuff that I like about Rust, which are different from C#, and I will present them to you. So you get excited. This is exactly what I want to have. And what should you do when you get excited? Well, together with the friends from Software and Support Media, I am glad to be one of the organizers and also one of the trainers at the upcoming Rust Summit in spring 2023. So if you want to learn more, if you want to really have a structured introduction into Rust, then that is exactly the event that you should take a look at. And with that, let's get rid of the slides. I promised you code only, and this is exactly what we are going to do. Let's make my video a little bit smaller so we can get started. Let's create a new Rust project, okay? Cargo is the tool with which we can create new projects. It's like .NET. This is not something that C# can learn from Rust because C# has the same. Cargo new, Rust is great. Oops, Rust is great. This is the name of the project, and oops, no. Rust is great, and let's fire up Visual Studio Code and open up the Rust environment here. Here we are. This is the source code, and this is where we are going to write a little bit of code. I pumped up the font a little bit, so hopefully you will see everything and everything will be okay. By the way, for those people watching me through remote, you can always ask your question using the chat. I have a window here on my second screen, so I see the live discussion. So if you have any questions, or if you want to clap or whatever, if you want to tell me that you also find this feature crazy good, then let me know, okay? I want to see a lot of emojis in the live discussion. And with that, let's start with the first chapter, and this chapter is constants. You might say, Rainer, C# can learn something from Rust in terms of constants. Constants are the most boring thing that a programming language can have, right? I bet you haven't seen Rust if you think that. For instance, let's define a few constants, and you will see me copying in a lot of code, so I will not type in so much. So the first two constants are pretty simple. They are just constants. Can C# learn something from Rust here? No. No, that is really, really very simple. Same is true for a string. We can put a string here. Okay, that's a string. But this is something for the first time where C# can learn something from Rust. And in fact, C# learned something. Maybe not from Rust, but it learned something. In the newest version of C#, we got UTF-8 literals in C#. And guess what? In Rust, such literals like that are UTF-8 literals. Exactly what we expect. So this is something where C# already learned, maybe from Rust. In Rust, it's also possible to do interesting things with ASCII-based UTF-8 constants, so single byte character constants. You can just write a B here, and what you will then get, you will get an array of unsigned 8. This is a byte. Unsigned 8-bit is a byte, and in this case we get a reference to this buffer, which consists of the UTF-8 buffer where this thing is on. Now I will have a lot of unused variables, and Rust always gives me a warning when I have unused variables. That is the same as in C#. Let's quickly disable that. We do that with the allow clause up here, and I just tell the system that unused variables are fine for the sake of this demo. Next thing, let's define a more interesting constant, and that is already something that is pretty amazing what you see here. This is an array of integer 32-bit. But the beauty here in Rust is that this constant array has a fixed size, and variables which are arrays are the same here in Rust. Arrays can live on the stack. That's a huge difference, and you will see me doing that later on more. So this is an array, and each array in Rust must have an exact compile time known size. This is what we do. We create a constant array. That is something that C# can't do in that way, right? So it's getting more and more interesting. Constant arrays are definitely possible in Rust. The next thing that I would like to show you will definitely blow your mind. Boom, see that? We have a structure, yes, a Rust structured data type, in this case a structure customer, which consists of name and age. Please don't worry about this thing. This is a so-called lifetime. It doesn't matter. That would be a Rust detail. We don't worry about that in this course. Essentially, it's like a class or a struct in C#. Rust doesn't have classes. Rust doesn't have regular polymorphism as you might know it from C#. Rust just has structs. Everything is built around structs. You will learn about more about that in this hour. And guess what we can do? Yes, you see correctly. We can, in Rust, define structured data types and define constants based on these structured data types. So what Rust will do, it will really create a constant customer, and the entire compiler platform will treat this customer as constants. If I reference the name or the age, it will treat these things as constants. So therefore, we get a lot of compiler magic, a lot of optimization, a lot of compile time calculation if we just use a structured data type here, in this case, the customer. So again, constants are way more interesting in Rust than they might seem in C#. But this is just the beginning. This is just the beginning. I have so many more things here about constants. Let me show you what the next stop in our journey is. See? This is a trait. Trait is in Rust similar to an interface in C#, but with way more power. For now, it's perfectly fine to think of a trait like an interface, and I define an interface here which is called has numbers. But the beautiful thing here is, and that's again something that C# doesn't have, and it could learn that from Rust, constants inside of traits. Remember, traits are interfaces. We can, on the one hand side here, require that a struct that implements the trait has certain constants, and we can also declare and define constants with default values directly in the trait, as you can see here. So we define a default value for this constant last number inside of the trait. Think interface in C#. Now, implementing an interface in Rust has a little bit of a different syntax than we have it in C#. In C# we would write class, blah, and colon, and the interface name. Here in Rust, we define the structure. In this case, I define an empty structure, It's essentially a class without members, or a struct without members. I called it I have numbers. It has no members, that's okay, but it implements our interface. And see, now the implementation of the interface has to have the constant, as you can see it here, and I can also, when defining this constant, refer to the constant which has a default value and comes from the trait up here. And then I can, for instance, use this I have numbers struct. This is a struct, not a trait, and I can directly reference the constants and I can work with it. Constants are super powerful here because the compiler will treat these things as constants. For instance, if I loop over these numbers and calculate the sum and print it, the compiler will do the calculation at compile time, not at runtime. So Rust is pretty awesome when it comes to those constants. Okay, you think we're done? Think we're done? I have one more. I have one more, a super powerful thing with which you can really give your application kind of performance boost. And this is done a lot in Rust, and every version of Rust is getting better and better in the next feature that I'm going to copy here into my code. This is the next feature. Please take a look. We have a function here. This function takes a so-called const here, a const generic parameter. That's the size that we want to create. And I think the code is relatively easy to read, even if you are not capable of, if you are not an experienced Rust developer. We generate again an array of numbers. This n parameter defines the number of numbers that we generate. Then we have a loop and we simply generate a counter. So first number will be 0, then 1, 2, 3. I think you get the idea, right? But the awesome thing here is this one. This is a const function. A constant function, and that means that this function runs at compile time and not at runtime. Yes, at compile time. The compiler will run the code during compiling. It's kind of code generators in C#, but on steroids. Now what can I do with that? I can, for instance, say generate 10 numbers by defining here an array of integers 32 with 10 elements. And what Rust will do, let me draw a little bit here. Rust will recognize that on the left-hand side, the variable is declared with a size of 10. It will pass in this 10 using type inference into our constant function and evaluate the entire constant function at compile time, and therefore we end up at runtime with a ready-made array of 10 consecutive integer numbers, and then we can access them. And there is a lot you can do in constant functions. You cannot do everything. You see that here. I, for instance, didn't use the for loop here. That's a limitation, for instance, of const functions. I'm not allowed to use for loops, but I'm allowed to use while. I can do string manipulation if I want. I can do a lot of crazy stuff. So const functions are really powerful. And as I said, they can be used to do calculations, generate values, generate arrays or whatever at compile time. Really nice, isn't it? So these are constants. I hope you've seen that Rust can do a lot here, and there are some aspects to it that C# can't do yet. Maybe C# learns new tricks over time, but with that, I will take that one, delete it, and go into the next chapter. So take a sip of your drink. Maybe you have a drink with you, because now we're going into the next chapter, which is called variables. By the way, if I'm too fast, and if you think, oh, that was interesting, but I have to take a closer look, don't worry. Of course, I have checked in my entire source code in GitHub, so you can take a look at the code in slow motion if you want on GitHub. And I also record this session, and I will put it in a few days on my YouTube channel. So if you follow me on YouTube, you will definitely get a video recording of this session. So, next stop, variables. Let's define a trivial variable. Okay, that's a variable. Very clear. What you see here, this gray I32, what you see here, I haven't typed that. That is the so-called Rust analyzer. The Rust analyzer always appends the type to the variable, but I did never specify the type. The type was inferred by taking a look at the right-hand side of the equal sign. Very similar to var that you know from C#. Now, the beautiful thing here is if I try to manipulate, for instance, this variable, this doesn't work. It simply doesn't work because variables in Rust, buckle up, are immutable by default. Yes, they are immutable by default. Immutability is a core concept in Rust. If I want to change this variable, I have to declare it as mutable. If it's not mutable, I cannot change it. And this mutability is not just a shallow immutability. For instance, if you have a vector, which is like a list in C#, and you define this list not as mutable, you can not only just not assign a new vector to it, but you even cannot push values into the vector because the vector is deep immutable. Okay, so having a very close, very tight control over what is mutable and what is immutable is super important and powerful, because then Rust can do a lot of compiler optimization. It can protect you from maybe critical sections, if you do multi-threaded programming and things like that. A lot of good stuff comes from the fact that Rust requires that you define your mutable variables with the mute modifier here. So let's get rid of it because we are not going to change this variable, so it's fine if it's immutable. Let's define another variable, let y. Let's make this one mutable. Mutable y equals 42. And now what I also wanted to show you is that I can use the suffix here to specify the data type. I could say this is an I32, this is an I64, this is a float 64, whatever I want to have. This is very similar to how C# does it. That is not really something very special. Last thing, I can also, if I want here, as you can see it here, I can specify the type explicitly, and we will need that in a second. So this is the basics. Now I've seen the basics, and now let's discuss the more interesting stuff. Let me disable GitHub Copilot because I don't want to have it currently in my environment. It always suggests things and maybe does some spoilering, and I don't want to have that, okay? So let's define a vector, a more complicated data type. A vector is like a list in C#. How could we create such a vector? We could, for instance, say vac new, and then we could say vector dot push 6, something like this, or 1 or something, whatever I want to do. Now this doesn't work. Why? Exactly, because I didn't define it as mutable. This is exactly what I wanted you to see. So the vector is deep immutable. I cannot change the content of the vector if it's not declared immutable. If it is declared immutable, I twisted that around. Now I can do that, but the interesting thing here is type inference. Do you see how powerful type inference works here? Here I define a vector. It would be like in C# to create a list without giving a type parameter here. And Rust says, okay, I'm chilling, it's perfectly fine. Rainer doesn't specify what this vector is all about. We'll see whether I can figure it out. And one line below, I have this push 1 here. And by looking at the calls that come afterwards, Rust solved this riddle and understands that this is a vector of I32. If I would, for instance, add a 1 as a byte here, the type of the vector changes. So type inference with variables and even complex variables is super powerful and goes way beyond what we are used to in C#. Now, this kind of filling a vector is kind of unusual in Rust. There is something else in Rust. What you typically do if you want to have a vector, you do something like this. And you will see me doing that a lot. And anybody happen to know what this is? What this exclamation mark is? Yes, if you are a C# developer, please don't start crying and shouting and leave the room. Stay here. It's macros. Yes, Rust is heavily depending on macros. Macros are all over the place. In all APIs, in all non-trivial APIs, everywhere you find macros. And this vector here does nothing else than creating the vector and pushing these values onto the vector. This is what this macro does. Don't worry, we are going to create the macro today in this session. But now you know, whenever you see me typing this exclamation mark, that means that I create a macro here. Okay, or I'm not creating a macro, I'm calling the macro. Sorry, getting ahead of myself. Now, next thing, regarding variables. Let's define a number, and this number should be 42. Maybe the user has entered this number through standard in or something like this. This is a Rust stir. A Rust stir is essentially a reference to a buffer where we have a UTF-8 string. That's a stir. There is also a string with an uppercase S in Rust, but that would be kind of string builder in C#. So uppercase string is like a string buffer that is not immutable, but this is mutable. This and stir, this is the string reference, and this is immutable. I cannot change it through this reference. Now, let me show you an awesome next line. Let number equal to let's call it, that's an i32, that's number. Then let's call the parse method here. Let's say unwrap or and specify a 0 here. What is this line? What's going on here? First, I would like to draw your attention to the fact that I have used the same variable 2 times with 2 different data types. This concept is awesome, and I would love to have it in C#. It's called shadowing. Shadowing. It's called shadowing. So you can use an identifier a second time, a third time, a fourth time inside the same function. Absolutely no problem. It doesn't do anything bad. It's just you saying, I'm no longer interested in this identifier and this value anymore. I'm simply reusing the name. We are recycling. Recycle, reuse, this is what we do. Rust is a sustainable language, kind of, by recycling names. This is what I do here. And to be honest, in C#, I have this concept pretty often. I get a value with the wrong data type, and then I use a helper variable, let's call it number as string, and then I need a second variable, number, which contains the parsed value, and so on and so on. In Rust, you simply don't need to do that. Just say let, and you're good. There are other interesting aspects here in this line. You see, we call the parse method here, but I never ever tell Rust what the target data type should be. I didn't say int.parse like in C# or parseInt like in JavaScript. Here we see again Rust's type inference in action. What Rust does internally, it says, okay, write a call the parse method. I have no idea into which data type I should parse. But then Rust takes a look on the left-hand side and recognizes that I declared the variable to be an i32. So therefore, it now knows, aha, Rainer wants me to parse this into an i32. And then it calls the proper method on the correct implementation of a certain trait so that it knows how to parse an i32. The beauty is, if I change that one, for instance, to float 64, nothing changes on the right-hand side. Well, yes, because I need to specify a different default value. If parsing goes wrong, I can use the unwrap or method to specify a default value. That is what I have to change. But at the end of the day, the parse call doesn't change at all. And that is really, really beautiful. That is super powerful. That is type inference. We're going to talk more about that in a second in Rust in action. Okay? And then obviously we can print line this guy, and this works as follows. Here we can, for instance, say the number is, and then we use these curly braces and we say number, and that will print the number on the screen. This is how we print something, and as you can see, even something as simple as printing something on standard out is a macro. See? So macros are really everywhere. So you have learned Rust variables are immutable. We have to declare them mutable. Type inference is super powerful with Rust. I showed you that with the vector, and I showed you that with the parse method, and you have learned a little bit about the type system in Rust. Let me quickly take a look at the live discussion. Stack allocated arrays are possible in C# via the keyword stack alloc. You are absolutely right. You're absolutely right, but you are limited to storing these things in spans and things like that. So you have certain limitations, but you are absolutely right, Ralph. C# can do that. So I was not 100% technically correct. You are correct. Okay, nice, good. Breathe in, breathe out. Variables done. Check. Next chapter. I would like to dive a little bit deeper into type inference. I will dive a little bit deeper into type inference. I already showed you the demo with the vector, so I can do a more interesting thing next. Well, we have to cover a little bit of basics here, otherwise you cannot follow the next samples. Let number, this is an I32, and then I say 42 and say parse, and I say unwrap. I don't specify a default value, so this will panic. We say Rust panics if I call unwrap and it cannot parse the value properly. So yeah, it's simply called unwrap. It's like getting a gift and you unwrap it and then you panic if you don't like the gift that you gotten. Yeah, this is how you can remember it. Maybe it's the 430th tie that you get at Christmas and you don't want another tie, and then you panic, and yeah, this happens after unwrapping your present. So remember, unwrap here. However, if I change this line slightly, let number equals to 42 and say parse and unwrap, then Rust has a problem, because now it has no idea what number is. This is shadowing, so this is not the previously defined variable. I have to change the syntax here, and for that I would like to show you a website. Give me a second. Voila! Do you see that? This website is called turbo.fish, and this is the name of the syntax in Rust that we are going to use now, the so-called turbofish syntax. And now you will never ever forget what turbofish is. Turbofish looks like that. I can specify the target type, the type parameter, like that. See? This is how I do it. And this looks a little bit, if I zoom in a lot, this looks a little bit like a fish. See, like a fish. And here at the end we have the, how is it called, flippers of the fish, where it can swim. Okay, so this is called the turbofish syntax, and you will see me using this syntax from now on sometimes. So this is an alternative to specifying the type on the left hand side. I can always specify the type parameter with this turbofish syntax, and you have seen turbo.fish, a great website to remember these things. So what will you take away from this talk? You will take away unwrapping Christmas presents. That's the first one, and you panic, and you will take away fishes. Yeah, a lot of little fishes. Turbofish. Okay, let's continue. The next thing that I would like to show you in terms of type inference is a function. Function, get values, this one, and I specify here that it should return a vector of I64, something like this, okay? And then I'm going to create let numbers, come on, should be a vector, 1, 2, 3, 4, something like this, and then we return numbers. Now, we have a lot of interesting stuff going on here. First, do you see that I didn't use a return statement? In Rust, if the last element of a function is an expression, and the expression does not contain a semicolon at the end, so it is really an expression and not a statement, then this is the return value. I could write return numbers, but this is very unusual and you should not do that. So please use this syntax in Rust. It's important. You will see that in a second why this is important. But the more important thing is that up until now, if I wrote a literal like that, the default type always has been I32. So if I define a variable, let x equals 42, then x will be an I32, a 32-bit integer value signed. But here, suddenly, it becomes I64. Why? What's going on here? Type inference goes on. Because what Rust says is, okay, Rainer specified here a bunch of literals, bunch of numeric literals, but I'm not quite sure yet whether this is an I64, an I32, or maybe an unsigned 64, or whatever. Let's wait, let's chill a little bit. Then Rust will recognize that this is an expression and it's the last expression of the function. Therefore, this guy becomes the return type. And suddenly it sees, oh, Rainer told me that the return type should be integer 64. So now, aha, I know that this one is an I64 literal. So it changes the value because of type inference. I could change that. I can say this is, for instance, here, let's say an unsigned 8, something like this. And suddenly the type of the vector changes. You see? So it interprets now this value differently. Yeah? And if I specify a value that is too large for unsigned 8, then I get an error, obviously. If I change that to 32, everything should be fine again, because now the vector is unsigned 32. So type inference is going way beyond what you are used to in C#. And I think that, yeah, C# could learn a lot from Rust here. So this is pretty powerful. By the way, I have to admit, it has a drawback too. Rust is not very famous for fast compile times. So if you have non-trivial Rust applications and you build them from scratch without having your caches filled up, you will drink a lot of coffee. Okay? Granted, you will drink a lot of coffee because all these steps that are going on here, they are not trivial. Yeah, they are not trivial. Rust is powerful, and once you compiled it, you have a lot in cache, and then everything is a little bit faster. But for instance, on a CI/CD server, on a continuous integration server, where you don't have caches filled up and everything pre-compiled, it takes a while. Yeah, and now you know why. The next sample, and this is the last example that I show you here in the chapter of type inference, is this beauty here. It needs an import statement. We need to import the hash map. We are here at a professional developer conference, so everybody should know what a hash map is. It's like a dictionary in C#, and this dictionary uses a dictionary key, which is a usize. Usize is processor-specific sized unsigned integral type. So it can be on my machine it's 64 bits because I have a 64-bit processor. And the payload is in this case very simple. It's just an I32. It's just an integer value. But the important thing goes on here. This is, ladies and gentlemen, LINQ, but in Rust. This essential LINQ. It's called iterators in Rust. So Rust is very strong when it comes to iterators. And for those of you who are professional C# developers and who have a little bit of LINQ know-how, it shouldn't be too hard to read this. We start with a vector, a list of integers. This turns this vector into a so-called iterator. It's like turning it into an IEnumerable. This is what's going on here. Now here I'm using a helper method, enumerate, which turns the values into a tuple where we get the index as the first element of the tuple and the value at this index as the second element. So item 0 is now the index, and here I map, it's like select in C#, I map something by multiplying it with 2. This is not something new. This is, you could even write that in a very similar fashion in C#. So here, C# is powerful, Rust is powerful. It wasn't difficult for me to learn how to work with iterators when I have learned Rust a few years ago. But the powerful thing is this one here. We start here from an iterator, and at the end we would like to have a hash map. But we don't use a method like toHashMap. That's not necessary. In C#, the IEnumerable would need to have a method or extension method that says toDictionary or something like this, but not in Rust. In Rust, we have a generic method collect that can collect in anything. I can collect into a hash map because here I have tuples of usize and I32. But I could also say that is a vector, and now I collect into a tuple of usize and I32, and now my entire data structure changed. It's no longer a hash map, it's a list, it's a vector of tuples, but the collect method didn't change. So again, very powerful when it comes to type inference. Collect takes a look at the result of the method and changes its behavior accordingly. Strictly speaking, technically, it calls a different trait. So everything is based on traits here. I will not go into the details about that. So I hope you have seen that type inference is a cornerstone, a foundation of Rust, and it goes a pretty long way. It's pretty cool, I think. Good. Haha. Are you still with me? I hope you are. A quick sip of water, and with that, we can go on. The next one is an easy one, and I think I will copy a little bit of code here because it's not that interesting. It's statements versus expressions. Boom. This is pretty natural. I'm defining a variable here. Integer 32 has a value. Then I have an if statement. Yes, the if statement doesn't have braces. Just say x equal 42, and then we print something. Nothing special here. But the next line is pretty astonishing. Boom. This is no longer an if statement. Now the if statement has become an if expression. Rust doesn't have the question mark colon syntax like C# for instance, or C, but Rust really has two natures of if. It can be a statement or it can be an expression, as you can see it here. Please note that the if expression here has here a code block, but this code block has as the last statement inside the code block an expression without a semicolon at the end. So this thing here becomes the return value, the data type of the if expression. So this if expression evaluates to an answer, so an immutable string here, because this if block returns an immutable string. Same is true here. Of course, I'm not allowed to mix things because then the data type of the if expression wouldn't fit. That's kind of obvious, right? And the blocks, they don't need to consist of a single line. It's perfectly fine to do something like print line here, I am here. Something like this. It's perfectly fine as long as the last thing inside of the code block is an expression without a semicolon at the end. Rust is perfectly fine and you still have an if expression here. So this dual nature of if and other statements is again very, very natural. It comes natural to Rust developers. It's really, again, a very important concept here in Rust. Now let me show you how far we can go by doing that one. In this case, I'm doing something which is very strange to C# developers. Ignore this one for a second. You see, I'm doing a loop, which is an endless loop. It's like saying while true in C#. Inside of this endless loop, I'm doing another loop. I'm counting from 0 to exclusive 100. By the way, this is how you define an inclusive upper range. Inclusive range, you know what I mean, and a thing which counts from 0 to 100 inclusive, yeah? And if I remove that, it's 100 exclusive. And if we have 42, I'm breaking. But what you see here, the interesting thing is, first, we can break loops based on tags. I can give this outer loop a name, I call it outer, and then I can break out of the outer loop, not just out of the for loop. We can discuss whether this is good practice, but it's definitely possible. But more importantly, we break with a return value. This I becomes the data type of the loop expression. It's not a loop statement. Take a close look. It's a loop expression because we are assigning the result of the loop to a variable x and then print this x on the screen. This is what we do here. And I could show you that for every statement in Rust. It works for a for statement, for an if statement, it works for a match statement, it works for all these statements. They can be used as statements and as expressions. Very powerful, and once you got used to this feature, you are going to love it. And whenever I I switch between Rust and C#, I always would love to see exactly that in C# too. Very nice. This topic was statements versus expressions. Breathe in, breathe out. New topic. I called it everything traits. Now we dive a little bit deeper into data modeling with Rust. Data modeling and object orientation. Because yes, definitely Rust is an object-oriented language, but it's not the object orientation that you might think of when you think of C#, for instance. Let's define a very simple structure here, and we call this structure vector 2D. It's a two-dimensional vector defined by an x-coordinate and a y-coordinate. Nothing special here. It is like a record struct in C#. Now what you see up here, you see this is again a macro, the so-called derive macro. You see, there is a trait. This is why I called it everything traits. This is a trait, the debug trait, and the debug trait says that a data type which implements the debug trait must be capable of turning itself into a string representation that is suitable for a developer. So this is not the display trait. The display trait would be the string representation for the end user, but the debug trait is for, as the name suggests, debug outputs, logs, something like this. And luckily, Rust has a powerful macro system, so I do not need to manually implement or generate the debug toString method, but I simply can say apply this derive macro, and the macro will generate the toString implementation of Rust to this structure. In Rust, it's not a toString implementation, it's implementing a trait, this debug trait. So the derive macro is very powerful because all these obvious implementations of traits, I don't need to write them. Rust comes with this derive macro and it will simply generate things like that. Do you want to copy such an item, deep copy or shallow copy? There is a derive macro for that. Do you want to compare a struct based on its members? There is a derive macro for that. And many, many other things simply come with derive. Okay, now let's add a bunch of functions to this structure here. Boom, a bunch of functions. This is how you add functions to a structure in Rust. So in Rust, you don't write the functions inside of the struct like you would in C#, but in Rust, you have a dedicated impl block. This impl block implements the vector, and this vector can have member functions or instance functions. This is like a static function here because it doesn't get something like this. Yeah, this would be an instance method because now it gets the instance of self as a parameter. But we don't want to have an instance method here. We want to have a static method if I stay in C# terms. So this is nothing else than creating an instance of myself, being the vector, and initializing x and y with constructor parameters. And just to demonstrate it a little bit better, I'm using here another construction function. I called it from slice. It gets a float32 slice. It's like a span, or in this case a read-only span in C#, where I do a little bit of checking, and you see if the length is not correct, I panic. Panic is not an exception. Panic is harder. Panic is red panic button, where I press on it and everything is meaningless from now on. We don't need to continue. Panic is way stronger than an exception. Something like an exception doesn't exist in Rust. So panic is stronger. Panic is a panic. This is exactly what I express here. I will show you later how we deal with recoverable errors. That shouldn't be panics. Panic is really, the world doesn't make sense anymore. Stop it. This is what panic is. Well, in this case, if we don't panic, we simply again create an instance and we get the values from the read-only span. In this case, it's a slice. So you see, nothing too difficult. Now we can define so-called traits. So we can go on and say, for instance here, let's define a trait. And by the way, you see correctly, I can define local structs inside functions. I can define traits like interfaces inside functions. Everything can be inside a function. So everything can be local. Another beautiful thing when it comes to Rust here. Now in this case, I'm defining a trait here, and this trait says whoever implements hasLength must provide a method length, and in this case calculate the length here. And it's pretty easy to implement that for the vector 2D because we are simply using Pythagoras and calculate the length of the vector. Nothing special here. It's really not difficult. Really not difficult what we see here. Okay? So, yeah. Clear. This is how simple traits work, and the syntax is different to C#, but at the end of the day, this is very similar to C#, so we can easily fold them up because syntax is a little bit different, but it's not really, really special. Now comes the special part. Let's copy this guy here. This is now a system trait. Rust is full of system traits. You can define the behavior of your structures by implementing selected system traits. In this case, I'm implementing one of the simplest system traits here. It's called default. Yes, you see correctly. In Rust, we can change the behavior of default. Not like in C#. In C#, default is a keyword. And the default keyword has a very special meaning. But in Rust, we change the behavior of default. So what we can say is, if somebody wants a default vector 2D, I simply create a new vector and I could specify every single value that is possible here. So in this case, I'm just using the default of float64, which ends up being 0, which is the same as C#, but I think you get the point. I can add anything here. And then, if I really want to have a default vector, I simply say here, default, default. I could, for instance, define that this has to be 1, 1, a vector with x1 and y1. This could be my default vector, and now I changed the behavior of default, and I get a vector 1, 1 here with this default thing. So that is the first one, and now we have seen how we can implement system traits. And I think you want to know more. I guess so. So let's add a little bit more here. Let's add. Let's add. Add is another system trait, and I think by looking at the code, you will immediately understand what this thing does. It allows us to implement generic math on top of structs. You know that with .NET 7, the .NET platform finally gets a possibility to implement generic math. You have this I support adding and all this stuff. Now I addable, whatever it is called. You get the system numerics namespace where we can define generic math on C#. So C# learned something from Rust. Rust was really defined based on these things. So the system traits change the behavior of operators and things like that. And if you want to add an operator, an indexer, or things like that, you simply implement the system trait like you see it here. But this trait, I selected it for this demo because it has another very powerful feature in Rust, which has no parallel in C#. In Rust, for traits like here, we can define additional named type parameters. So the add trait, I can show you how the add trait looks like, has a mandatory output type parameter. This mandatory output type parameter has to be specified here. So we have to say, if I add myself to another self, then the output in this case is self, and that is exactly that type up here. So named type parameters for traits is very important, and you will see Rust using that very extensively, especially when it comes to iterators. It's kind of a strange syntax. In C# we would add generics here, but in Rust this is more explicit. We really can define something that is very special. I can write documentation for it, so it's more expressive than what we have in C#. So type parameters for traits here. But yeah, takeaway, please. If you want to change the behavior of Rust, of default, of plus, of minus, operator overloading, everything is based on traits. Okay, the next one is a larger one, and please excuse that I will not walk you through the entire code, but I will try to make my very best so that you understand it. The first thing is just an enum, as you can see it here. It's an enum. You know what an enum is. Enum in Rust is way more powerful than in C#, but this is just a regular enum as you would also define it in C#. But now we have another system trait here, the fromster. The fromster trait. The fromster trait demands that we take a str, which is an UTF-8 string, and we return a result. And now it becomes interesting. What is result? Result is an enum, believe it or not. In Rust, enums can have parameters. I will show you. My last demo will be a larger demo where you see enums in action. For now, just remember it's an enum, and this is the basis of recoverable errors. So the result either returns error, this one, then something bad happened. And in our case, we use the enum as the error type. That is kind of a custom exception in C#. In C# we would need to create a class to define a custom exception type, but in Rust we don't do that. In Rust we use result, and here we specify the type for the happy path, in this case the vector. If everything is okay, we can provide a vector. But if something goes wrong, we can provide any type we want as being our error payload. Do you want to have just a string? Then I could write str. Do you want to have just an integer? I could write integer. Do you want to have the parse error, as you have seen before here? Then we can define any type that we want. We can define a struct. Usually it's an enum that you return here. And there are great crates. Crates are like NuGet packages, which help a lot for defining those results. For instance, this error or anyhow and so on. Very powerful crates which are used all over the place. Now let's take a look at the implementation of this fromster. We are using a split method here, but in contrast to C#, this split method does not copy anything. Split, on the contrary, just returns an iterator over char. Over the data type split. So what we get an iterator where we can iterate over slices. So it's not like split in a C# string where it copies things. It's really just like split on span. You can build that in C#, granted, but it's not there out of the box. Then I'm parsing this thing, and this is kind of interesting what you see here. We take the parts, and then we manually say next in a loop, because I have to say next 2 times. The first next positions our cursor on the first element, and now I do something interesting. I say OK or, and then I can specify the error type and the question mark. This question mark here tells Rust if an error occurred in this part of my link statement, then stop it here and return this error type. This is the question mark operator that bubbles up the error without me having to write an if statement. I can continue with the rest of the iterator statement of the kind of link statement and try to parse the thing that I got. And again, I'm mapping the error. If parse didn't work, if I got an error from the parse method, I map this error to my domain-specific error and use the question mark again. So if we have problems in the middle of a link statement, I can easily stop the rest and bubble everything up. Think of what you would do in a link select statement where you would try to parse something, and then inside of the select statement you find out that you have an error parsing this thing. How would you terminate the link statement, return the proper result code? This is beautiful, isn't it? I really think that this is beautiful. And what can we do with that? This is the kind of syntax that this fromster allows us to do. We can simply say, give us a string, 1 and 2. It will split based on the comma. I will call parse. Parse will recognize the vector, and everything is okay. And if I, for instance, do that one, this one will give me a runtime error because I call unwrap and this will panic, but it will panic with the correct error. In this case, it would panic with the too few elements because I only have one element and I didn't find a comma. I think you got the idea now, yeah? I hope so. So result is really the cornerstone of recoverable errors here. And this question mark operator, it's a dream come true, and you can write the error handling becomes so much easier, even if you don't have exceptions here. Okay. I take a look at the watch. I have 5 minutes. And I will probably use a little bit more than these 5 minutes, only a few minutes. Please excuse if I use maybe 7 or 8 minutes. I hope it's okay for you. So we can have a discussion afterwards, but yeah, I think it will be fine. I will copy the last example completely onto my code here because I will not walk you through most of this code here. Let me quickly add some usings here so that we have gotten rid a lot of the things you already know. So far you should already know what this derive is. I told you that, but now here you see some aspects I would like to pick out. Here you see an enum, you see, and this enum is now very different from a C# enum because now we can define that in case this enum is occupied, this enum has a parameter. But this is a tic-tac-toe game, by the way. So if a cell is occupied, then it's either occupied by X or O. Makes sense, right? If it's empty, I don't have payload. If it's occupied, I have a char. And this is what you can do with enums. And additionally, what you can do with enums is you can do everything you can do with structs. Enums are like structs. You can add functionality. You can implement traits. You can add operator overloading with implementing add and things like that. Enums are fully blown data types which have a lot of possibility. So in Rust, you will end up often you will end up writing enums instead of structs because they are so powerful. Many of the things that follow now, we already discussed it. We discussed methods and so on. We discussed how we implement system traits. This is a system trait for type conversion, for instance. We already discussed how to copy something or convert something from a string. It's just a little bit of Rust code. It's not that interesting. This is another thing why I put it here, this example, because in this case, I wanted you to show that it's again a system trait with which we can define an indexer on a data structure. So if we have our tic-tac-toe board, we want to have a custom indexer based on the data type board index. And let me quickly show you the board index. The board index consists of X and Y, so 2 coordinates. So we need a custom indexer to find the correct thing. And this is again done by adding a system trait. So also defining indexer, read indexer and write indexer have to be implemented separately, can be implemented by adding traits. Now you should really understand that in Rust everything is about traits. If you want to influence the behavior of your type in terms of language, indexer, plus, minus, operators and so on, add a trait. And this trait has winner is the second last thing that I want to show you. I have two things more and then we're done. This trait is not very difficult. It says it's a has winner trait. You can call the winner function and it will give you an option. Option can either have a value or no value. It's like result, but only with 2 things. Either we have something, some character, X or O, or none. These are the 2 options that you have here. But please take a look at this pure thing of beauty here. What we do here is we implement the has winner trait, which is an interface, for all types which have an indexer where I can get a square content using a board index. Wow. We can implement interfaces for all types that implement other interfaces. We don't need to implement the interface explicitly on a struct. We can say if this class, this struct in Rust, is already capable of doing something, in this case the index, I can derive more powerful capabilities from it by implementing traits on traits on traits. And everybody who has this index capability, this index trait, also now has the has-winner trait. So all the different implementations that maintain a square content and that can give me a square content based on an index, they now have the has-winner implementation, which is just a bunch of if statement because it's a tic-tac-toe game. But conceptually, this is pretty astonishing, right? So traits are powerful. And this is the last thing. I saved the best for last. Let's define a macro at the end. Macros are really crazy in Rust. It's crazy what you can do with Rust. This macro here defines a tic-tac-toe domain-specific language. Yes, you can go out of this session and say, we built a domain-specific language for tic-tac-toe. What you see here is that I define a so-called abstract syntax tree, essentially a syntax tree, a grammar inside of Rust. I say I have some constants here, and then after some constants I get a literal, and then I get another literal, and from all these literals I generate a board. Do you want to see how we use this macro? Here it is. This is now a tic-tac-toe domain-specific language inside of a Rust program. Yes, we can do that with Rust. We can really add custom structures, custom languages. We can build whatever we want. We have so much possibilities with macros here. If I screw something up, I definitely get a compiler error because the Rust compiler does the compiling for us. The Rust compiler is a kind of compiler. It will analyze the syntax tree. It will recognize whether I screw something up. It will do type checking. So if I say, I don't know, 42 or something like this, it will tell me that this doesn't work. This is not a character. Please give me a character here. So you see that macros go way beyond simple string replacements. So I saved this thing for last because this should show you that we just scratched the surface on Rust macros. And if you take a look at Rust libraries, web API frameworks, WebSocket frameworks, file APIs, and so on, a lot of them are based on macros because it's such a powerful thing that saves us from writing a lot of code manually. And that's it. That's it. I overshot by 3 minutes. I hope you aren't angry, but Rust is so cool, and I hope it was an interesting and also a little bit funny evening here together, taking a look at this Rust language and finding out how it differs from C#. Have you seen everything about Rust? Absolutely not. I could go on for a week if you want, because there is so much to learn and so much to discover here. I randomly picked out things which I thought were interesting, and I hope you agree. Thank you very much for watching. Thank you very much for attending, and let's open it up for questions if there are questions. Thank you for having me, and for those of you who would like to leave before the Q&A, bye, have a nice evening. See you tomorrow maybe at the Q&A at the Ask Me Anything that we have tomorrow in the evening, where I will also participate. So, questions.